Well, hey there, this is Mrs. Sharp, and since my voice is not doing so well today, I decided to go ahead and record a video so that instead of trying to say this every hour, I can maybe keep my voice and still get you guys the notes that you needed. So we're continuing our discussion today of Learning Target 2.1. We talked yesterday about the law of conservation of energy, and we're going to come back to that. But I want to switch gears for a second to talk about phases of matter. So I want us to talk about what atoms and molecules are doing in different states of matter. So we're going to talk about kinetic energy, shape and volume of these different solids, liquids, and gases. So first of all, for the kinetic energy of solids, the molecules and atoms are tightly packed, but they're still moving. In fact, the only time matter stops moving or has zero kinetic energy would be at absolute zero, which is 0 degrees Kelvin. So they're still moving. They're more doing like a vibrating against each other. Solids hold their own shape. They do not take the shape of containers. So you know that if you took a lump of carbon, for example, and you put it into a container, it wouldn't take the shape of that container, it would just sit there. That's a property of a solid. Solids cannot be pressed into a smaller volume because of the fact that they are tightly packed. We call that incompressible. So their volume cannot be compressed. However, the volume of a solid will increase slightly when heated. And you guys know that if you've ever had like a door stick in the summer, where it opens just fine in the winter, but in the summertime when it gets warm in your house, the door sticks. That's because those molecules are expanding just a little bit, enough for that door to stick. Okay, so those are properties of solids. If I were going to draw this at the molecular level, just have like a little container here maybe, and those particles would be packed nice and tight all against each other, and they're usually pretty uniform, not always. They're packed in there and they're kind of just vibrating up against each other, but very tightly packed. That's a solid. Should be pretty much review stuff you already know. Let's talk about liquids. In liquids, molecules or atoms are able to move past one another. They flow and they take the shape of their container. Liquids also cannot be pressed into a smaller volume. They're incompressible, just like a solid. So even though they take the shape of their container, it's not possible to make them occupy a smaller amount of space. Their shape might change, but the amount of space they actually take up is going to be the same. Liquids also increase in volume just ever so slightly when they are heated. Here's what we mean by cannot be compressed and take the shape of their containers. So here's a liquid. If this is 20 milliliters and I dump it into a really shallow, let's say, dish, the shape is going to be different, but that's still going to be 20 milliliters. So the shape is going to change, but it's not going to take up any less or more space because of that shape. The only time it might take up just a little bit more space, not even enough to really measure, would be when those molecules are heated, they have more energy, and they sort of spread out from each other. So a liquid, in relationship to a solid, is a lot more spread out. So they do tend to like bump into each other every now and then, but they're sort of moving and bumping into each other and then going right past each other. There's not a lot of space in between them. And notice I'm drawing this kind of randomly, but they have space to move and flow past each other, but they're not restricted in their movement. This ability to flow is because of what's called transients. of the atoms and molecules. Transients. It means they are sometimes together, sometimes separate. They're transient. So if they're together, they'll probably separate later on. When they get heated up, they just have more energy to bounce off of each other, so they're able to spread out just a little bit more. Okay, let's talk about gases. Last one. Gases, the molecules or atoms in that gas will move to fill the volume of the entire container. So they're going to spread out from each other as far as possible. They can easily be expanded and compressed by changing temperature or pressure. So unlike a solid or a liquid, which cannot be compressed at all, it's pretty easy to compress a gas. A gas can also easily be expanded, not slightly, but a lot. Gases take the shape of their container as well because they spread out to fill that volume of the entire container. At the same time, their volume is able to change. The molecules and atoms in a gas are extremely far apart. They have the highest kinetic energy of all three phases. Okay, so I'm going to pause for a minute here. Okay, here we go. I have a little animation to show you here. Let's see. All right, now we've got it zoomed in a little bit. Here's the solid. This is water. So the two hydrogens for H2O are gray, and the red is oxygen. And you can see here they're sort of locked into place, and they're vibrating. So they do have kinetic energy, although they're not bopping around too much. They're kind of locked into place. I would argue that in this animation there really should be a little bit closer together, but in water is weird, and for some reason when it's a solid it spaces out from each other more than a typical solid would. So water is spaced out more in the solid form than most. Here's the liquid. You can see the difference. Look at the transients. They sort of bump into each other and then separate, and they're free, and they bump into each other again and become free. So lots more kinetic energy, faster movement than here in the solid state. And finally, in the gas state, lots of kinetic energy, no transients, not really bonded together or bumping together too much. When they do bump together, they go separate immediately. There we go. Just wanted to remind you, you do not have to write this down again because you should have it in your notes. But in a phase changes are going to do one of two things. Either they're going to require or absorb energy, which would make that phase change endothermic. Remember, that's what endothermic means. Or they're going to release energy, which is exothermic. And remember, we're not talking heat. We're talking energy. So requiring energy means it's endothermic. Releasing energy means it's exothermic. One more thing to add to this before we talk some more about phase changes. We need to define these things called the system and the surrounding. So this can continue to go in your notes underneath how does energy change during phase changes. We need to define two things. One is the system, and the system is the specific part of the universe that contains the reaction or process being studied. It's called the system. That's what we're interested in. The surroundings is everything else in the universe, which is huge. So according to our definition in chemistry, the universe is the system plus the surroundings. All we care about is the system for deciding if something is endothermic or exothermic. This helps us get a perspective of which way energy is flowing. So if we want to take water as an example, maybe a pot of water on the stove. Here's my pot, here's my water, and here's the burner. So let's say I want to boil this water. In this example, if we're concerned with water, water is the system. We want to know what's happening with the water. So the surroundings would be the pot, the burner, the air around the pot, everything else in the universe. We don't care about anything except for the system. So when I heat up this water on the stove, energy is going to be flowing from the burner into the water. So from the perspective of the system, energy is flowing in. In energy means it's endothermic. So water is gaining energy here. So, and from the water's perspective, energy is coming in. It's an endothermic process. But for the burner, if I was thinking about the surroundings, energy is going out of the surroundings into the system. So for the surroundings, that would be exothermic. Because for every time you have an endothermic process, that energy has to come from somewhere. So for the surroundings, it's going to be the opposite. That's why we have to pick something to be interested in and gain perspective. So let's talk about this in terms of phase changes. On the next page, you have a few boxes that look like, well, just boxes. Mine look fancy. I want you to write in those boxes on the left-hand side, solid, liquid, and gas. Now for solid, liquid, and gas, as you increase up this process, you are increasing the amount of kinetic energy. So kinetic energy goes from lowest to highest, or least to most. Okay, so we could even do a scale, like this is 0 joules, maybe this is 100 joules, and this is 1,000 joules. Okay, so we're just making up those numbers. They're totally random. Okay, so if I was doing a phase change that went from a gas to a liquid, that's called condensation, regardless of what it is. It could be water, it could be carbon dioxide, it could be anything you want. If it goes from a gas to a liquid, it's called condensation. Going from a liquid to a solid is called solidification. I know you want to call it freezing, but the technical name for it is solidification. Going from a gas to a solid is called deposition. Now notice we always went down in kinetic energy for each one of these. So there's all three again. Each step is a decrease in kinetic energy. So every time we're going down in kinetic energy, which means we're going to have some energy left over, and that energy is released. So for example, we said that this is 1,000, and we just totally made up that random number, but we know it's higher than what it is for a liquid. If I condense from 1,000 to 100, final minus initial is my change in energy. So I had 100 joules, final energy, minus initial energy, is 100 minus 1,000. So I went down 900 joules. That 900 joules has to go somewhere. It goes to the surroundings. If that goes to the surroundings, that 900 extra joules is going out of the system into the surroundings, out of system. That means that each one of these is an exothermic process. Exo, exo, exo. Every single one of these would result in having extra energy left over, which would go out to the surroundings. If it goes out of the system, out energy, then it's exothermic. That energy is released. Go back there for a second. energy is released, extra energy is released, so it's exothermic. Let's look at the other side of this. If I still am going from solid, liquid to gas in amounts of energy, vaporization is going from a liquid to a gas. Fusion or melting is going from a solid to a liquid. And sublimation is going from a solid to a gas. I'll get them all up here again. This time, each step is going up in kinetic energy. So we need to get that energy from somewhere. Where is it coming from? The surroundings. That's the outside source. So if energy is coming in from the surroundings, energy is absorbed. That means the extra energy has to be absorbed from somewhere, so this is an endothermic process. The extra energy is coming in from somewhere. We're not just all of a sudden going to like randomly have more energy. The energy has to come from somewhere. So again, if I want to go from 0 joules to 100 and going from a solid to a liquid in the process of fusion, I'm going to need to go 100 minus 0, final minus initial. I'm going to need 100 joules. I'm going to need it from somewhere. So I'm going to have to get it from the surroundings. So that's all for today. Thank you very much. Have a wonderful day.